Hello. So today we will study what mechanism of reactions, that is SN1 and SN2 in case of your substitution reactions. So what is SN1 and SN2? Well, SN1, S stands for your substitution, N stands for your nucleophilic, and 1 stands for your unimolecular. Similarly, in case of SN2 also, S stands for your substitution, N stands for your nucleophilic, and 2 stands for your bimolecular reaction. So simply we can write this is unimolecular reaction, this is bimolecular reaction. And well, what happens in case of SN1 mechanism? It happens so that it takes 2 steps to complete the substitution reaction. What happens? Let us take for example, like it is ethyl bromide, that is CS3CS2Br. It first undergoes the formation of CS through CS2 plus, that is the carbocation, and plus Br minus it forms. Then after what happens? So we'll see that here it is the slow process, and the second step is the attack of the nucleophile. So it attacks here CS3CS2 plus OH minus, it is the carbocation plus OH minus gives ethyl alcohol. This is actually a very fast step, and this one is the slow step. But in case of if you see in the bimolecular, that is SN2 mechanism, then only one step takes place. How the one step takes place? Because here an unstable intermediary compound is formed, unstable, which actually disintegrates and gets converted to the alcohol whatever we want to produce, that is the attacking nucleophile. Okay, so if you see, if you take ethyl chloride plus OH minus, it gives an intermediary compound, that is CS3CS2. Here Cl1 Cl will be there, here another OH will be there. So what happens actually? Here it is the alpha alpha carbon atom. Okay, this one is alpha carbon atom. So this one actually, the OH, it sticks to the carbon, this alpha, it attacks to the alpha, and this Cl, it disintegrates. Now here it is formed CS3CS2OH plus Cl minus. If we want to know the rate, well, the rate here is, as we know, the rate determining step is Cl, that is the slowest process is known as the rate determining process. So rate here comes K, this is rate is concentration of CS3CS2Br. Whereas here, what happens? There is no rate determining step, there is only one step. So here the rate is this one is the reactant, so their concentration. So definitely it became first order reaction and it became second order reaction. So this is the reason why also, this is one of the reasons, I am saying you one of the reasons, because one is unimolecular and second one is, this is one of the reasons, this is first order reaction, so this name is given SN1 mechanism, whereas here it is the order is 2, so this is second order reaction, so here it is given bimolecular. Okay, now regarding stability, if we see here, these carbocations, that is 3-degree carbocation, it is more stable than your 2-degree carbocation, then it is more stable than 1 degree. Whereas in case of bimolecular or SN2 mechanism, if we see, then 1 degree is more stable, then here comes 2 degree, then comes 3 degree. Okay, here 1 degree is more stable than 2 degree is more stable than 3 degree. Well, there is a question it is asked, why in case of SN2 mechanism 1 degree is more stable and it is easily, the substitution reaction undergoes easily, whereas in case of your SN1 mechanism, the substitution reaction undergoes easily with the 3 degree. What is the reason? Why? Well, you can write it, just note it down. Okay. In case of SN2 reactions, The attack on the nucleophile, the attack on the of the nucleophile occurs from the backside on the alpha carbon. Occurs from the backside. Backside, how it forms. Backside. See, here if we see the 3D orientation, then H is there, here Cl is there in the back, here it is another H is there, this side alkyl group is there. So what happens? The attack of the nucleophile, that is OH minus, is from the back to the alpha carbon atom. This is the alpha one. Okay. So alpha carbon atom, these are the alpha and this one is beta. Okay. So the second carbon atom that is added to the alkyl group where the halogen is attached, that is known as beta, and the first one to which the halogen is attached, that is known as alpha. So the attack is on the right. In SN2 reaction, the attack of the nucleophile occurs from the back on the alpha carbon. Therefore, presence of bulky substituents near the alpha carbon tends to hinder the approach of the nucleophile, to the alpha carbon due to steric hindrance. Therefore, 3 degree has more steric hindrance than 2 degree than 1 degree. Okay. So greater the steric hindrance, slower is the reaction. Therefore, 1 degree undergoes substitution easily in case of SN2 mechanism. Okay. Whereas in case of SN1 mechanism, right? Whereas in case of SN1 mechanism, the stability of the carbocations are in the order 3 degree, that is greater than 2 degree, is greater than 1 degree. 3 degree is greater than 2 degree, is greater than 1 degree. Due to electron releasing groups, more electron releasing groups. Okay. Hence, the 3 degree undergoes SN1 substitution under SN1 mechanism easily. Okay. Then after we'll move to your optical isomerism. Okay. So this is substitution SN1 SN2. So next we'll study about the optical isomerism. So what is optical isomerism? Optical isomerism माने कौन? Suppose optically active, optically inactive. Suppose if this is the mirror, let us say this is the mirror. If I am keeping this hand here, so this hand will look like how? So like this only, like this only it will look. But if I want to, it will look like this. Do you think so? Hello? No? Yes. So these are exactly impossible. superimposable. Okay, but what happens, you see, if I take this hand, and this hand, okay, these are mirror images. If I take them separately and I superimpose them, then do they superimpose? No. There is this is known as optical isomerism. Means the structures are same, the orientation are same, but when they are actually optically viewed, then they are not superimposed. But sometimes they are superimposed, and that is known as optically inactive, whereas when they are not superimposed, they are known as optically active. Okay, optically active. So in case of optical isomerism, see, so we know that what happens actually through every molecule or through every substance, when we pass the light, polarized, there is polarization occurs. That is the polarized light when it is passed through. Okay, so everything rotates, the substances, it rotates the isomerism, rotates the polarized light. Okay, so everybody try to understand what is polarization. Okay, try to understand yourself what is polarization. So it rotates the plane of plane of a polarized light towards left or right. Towards left or right is called optically reactive. When a compound rotates the plane of polarized light towards left or right, then it is called optically reactive. Suppose if we say what is plane of polarized light, so plane of polarized light means plane of polarized light. So we know that in a substance, the light, it actually passes through each and every direction. But when it is passed through an upper prism, okay, this is the prism, okay, this one is known as Nicol prism. So this one, when it is passed through Nicol prism, so this becomes either right or left. So what is Nicol prism? Well, if somebody asks, then it is the prism made up of crystalline calcium carbonate. Okay, that is the prism that is made up of crystalline calcium carbonate. So when light passes through the Nicol prism, then what happens? Here we get the polarized light. Okay, that is, we get something like this. So if it turns left, if it is in the left direction, if it is like left direction, or right, we can say like this. So these two have different names. That is, if it is in the right, then it is known as dextrorotatory. If it is in the left, then this is known as leviorotatory. And this is known as dextrorotatory. This is often, it is said as L and it is taken as D. So when the polarized light, after it passes through the Nicol prism, then after, if we get the polarized light and if it is turned right, then it is known as dextrorotatory, that is D. And whereas in case of when it is rotated left, then that is known as leviorotatory, or it is otherwise also called as L. Okay, so Like this, if we want to find, suppose we have taken a mug, okay. Suppose we have taken a mug like this with the handle at this side, and we take the mirror image. So now how the mirror image will come? Mirror image will come this side only. So like this, what happens? Here if we put these two figures, then how they will superimpose? Like this only. So like this only, because here the handle is this side, here the handle is this side. If we take the image and put it here, then the handle is in this side. So whenever the image, those two objects, they are superimposable, so they are known as non-superimposable mirror images. So when optically active, they are non-superimposable mirror images. So when optically active, so these are known as non-superimposable mirror images. See, but what are optically inactive? For example, if we take O, then if we see the image, then it is O. These are superimposable, so optically inactive. If I take A, let us say A, then here it is also formed A. These are superimposable. So these things are known as optically inactive when they are superimposed. When they are superimposed. Got it? So next here, in case of optical isomerism, so in case of SN1 and SN2, now we'll see, we know that what is optical isomerism. So as when a polarized light to jatoda mein pass, when we pass it, so rotates the polarized light towards left or right when it is optically active. But whenever it is optically inactive, it will stay like this. Okay? So now if we want to see, like let us take for example, if something as like chiral carbon atom, okay? So when we take the case of chiral molecules, okay, chiral molecule means whenever this is a chiral molecule, this is a chiral molecule, okay. So chiral molecule means one asymmetric carbon atom is there. So asymmetric carbon, see here it is quite asymmetric because here C2H5 is there, here CH3 is there, so it is asymmetric. So these type of chiral molecules, they are optically active. What happens if we see the mirror image? Then it will be something like this. It will be formed here, it will be formed here, and if we take superimpose, there is no superimposition. That is completely different. So these are optically active. We take we take butan-2-ol. This is butan-2-ol, and if we see the mirror image, it will look like this. Okay. First, let us try to understand how it forms. Okay. Let us say, yeah. So this is the carbon. Okay. And suppose if you take this one is the carbon, and to it actually here this side hydrogen is attached. Here this side you have got OH minus is attached, and here this side it is your this side. It is the back side is your ethyl molecule, that is CH2 CH3, and the front side front side is your CH3 group it is attached. Whenever we see this in the mirror, then what happens? This is formed like this. This is formed like this. This is the CH3. This is the C2H5 or CH2CH3 molecule. This one is H and this one is OH. So this is the front side, here it comes the front, this back side, here it forms the back. Okay, so if we see the 3D back side, front side, then these are non-superimposable. So this is also optically active. But if we take non-chiral molecules such as, so this one simple butanol, or this is propan-2-ol, this is quite symmetric, so there will be no optical isomerism, so we can say there is no rotation, so they are optically inactive. Okay, so coming back to this with optical isomers, if we come to your SN1 and SN2, well, when in case of SN1, then the dextrorotatory, there is no configuration change, so there is retention of configuration and the D remains as D only. In case of, like, see, this is butanol, or if you say propan-2-ol, then these things actually they undergo SN1 mechanism, because here they are optically inactive, they remain as such. But whereas when we take these things they undergo, when they are optically active, so they undergo SN2 mechanism. In case of SN2 also, what happens actually? See, there is dextrorotatory to D to L and L to D. If it is L, then to D. If it is the polarized light is towards left, then after after SN2 mechanism, it is right. So there, in that case, there is inversion of configuration is there, as well as if it is from dextrorotatory to, suppose there is 50% of levorotatory and 50% of dextrorotatory. So what happens? This becomes optically inactive. Why? Because 50% of what? Levorotatory, your left side, 50% of dextrorotatory, right side. So right and left, they cancel each other. This type of mixture is known as, racemic mixture. Okay, this type of mixture is known as racemic mixture. So write what is racemic mixture. You can write if you want, like racemic mixtures, a mixture of equal amounts of two enantiomers, a mixture of equal amounts of two enantiomers is called racemic mixture. It is optically inactive. Okay. Then after, if we want to so then another one is that here at the last, if you see, then we come to the resolution part. Resolution. Now what is a resolution? Resolution means it is to separate. It is the process of separation of D and L from racemic mixture. The process of separating the DLL from racemic mixture, it is known as the resolution. Okay. Then after, we'll move to your elimination. Substitution part is over. Now we'll move to the elimination part. Now elimination reaction. So elimination reaction, the second one, that is elimination reaction. It is otherwise also known as beta reaction. Just now I told you what is alpha and what is beta. Okay. Wherever the halide ion that is attached to the carbon, that carbon is known as alpha, whereas the carbon atom that is situated adjacent to the carbon atom, that is alpha, situated adjacent to alpha, it is known as beta. So it is also known as beta reaction, or you can say beta elimination. Okay, beta elimination. Suppose for let us take for first one, that is dehydrohalogenation reaction. So what is dehydrohalogenation reaction? D means removal. Hydro means that is the H part, and halogenation means that is X part or halogen part. So now H part we will remove and also X part we will remove. So how come it is possible? See, and how it occurs, that we will be seeing here. In case of dehydrohalogenation reaction, let us take for example CH3CH2Br. CH3CH2Br in the presence of alcoholic KOH. So in the presence of alcoholic KOH, it gives CH3. Now what happens actually? See, there aqueous KOH in the substitution reaction we had used aqueous KOH. So in order to get the ethyl alcohol part, whereas here we are using alcohol KOH. So here we will get what? That is ethene, CH2 double bond CH2. How come it occurs? Plus HBr. So what happens exactly is, one hydrogen, that this is alpha and this is beta. So this beta part, it will lose the hydrogen. It will lose the hydrogen and it will form double bond. It will lose the hydrogen, that's why it is known as beta elimination. Beta parts, beta carbons, hydrogen will be getting, it will be removed. So dehydro means, D means removal, hydro means hydrogen. So this hydrogen, which one is removed, it is halogenated. So halogenation. Got it? So CH3CH2Br, alcoholic KOH. So here this beta carbons, hydrogen is detached. So there is dehydro, then it gets halogenated with Br. So it forms CH2 double bond CH2, that is ethene or alkene plus HBr. Okay, clear? Then after, actually see, if we want to ask, then it follows Set-Zev's rules. There is one rule that is known as Set-Zev's rule. Set-Zev's rule. Okay. So Set-Zev's rule. What does this rule state? See, if two beta are there, if only one beta is there, okay, fine, you will go with Set-Zev's rule. Or just like the simple form you will go. But whenever there is two beta, then what you will do? It will undergo Set-Zev's rule, or it has to follow Set-Zev elimination. Now what is Set-Zev's rule? Set-Zev's rule, right? If the halogen, Set-Zev's rule. If the halogen is present on any carbon atom within the chain, if the halogen is present in any carbon atom within the chain, the alkyl halide can undergo dehydrohalogenation in two or more different directions depending upon the number of different types of beta hydrogen available. In all such cases, the more highly substituted alkene, that is having lesser number of hydrogen atom on the doubly bonded carbon atom, is the major product of dehydrohalogenation. This is known as Set-Zev's rule, and this mode of elimination is known as, it is Set-Zev elimination. Okay, suppose let us take for example, here we take, let us take like there are two carbon atoms. Okay, so two, like if we take CH3 CH2, CH, here chlorine is there, here CH3 is there. Okay. So now which one is alpha here? So you will see that. Okay, let us take here. So this one is alpha 1. Let us take this one is beta 1 and this one is beta 2. So according to dehydrohalogenation reaction, it can take either the hydrogenation, dehydrogenation can be done from this beta or this beta. Okay, let us take it form two compounds. That is, first one is, let us take, it takes from beta 1. So beta 1 hydrogen removal is there. So what will come? CH3, CH2, CH double bond, CH2. Now here one hydrogen is removed and this Br is attached. Now in case of beta 2 elimination, what happens? So here CH3, CH double bond, CH, CH3. Okay. So see, here two products are formed, but one thing must be major and another one must be minor, right? So the more symmetrical, what I said just now in Saint-Jeff's rule. In Saint-Jeff's rule I said the hydrogen, which one is more stable? Having less number of hydrogen atoms on the doubly bonded. Here there are, see, in the doubly bonded, here there are more hydrogen, whereas here we see that there is lesser number of hydrogen. One is attached, and also it is symmetric. So this is the major one, major product form, and this one is the minor product form. That is, it is formed in lesser amount. Okay, both the products are formed, but it is formed in less. So this is known as, if you want to see the ease of dehydrohalogenation, ease of dehydrohalogenation. If we see the order, then we will see that it is R2C double bond Cr2. It is the stability. See here the stability is higher, so it will be formed more. If you see, then we can see that it is RC double bond Cr2. Okay, RCH double bond Cr2 is just greater than RCH double bond CHR. Okay. This is the